Okay. Okay, we're Team Colossus. I'm Thomas, and I did the electronics.
I'm Ashwin, and I'm head of software engineering.
I'm Ben, and I was head of structural design. I'm also Ben.
I'm Monty. I was head of outreach, and I sort of helped a bit with the software and electronics because
We're Team Colossus, and we split into 3 main groups: electronics, software, and structural design. We all worked as independently as possible, where we met up regularly to coordinate things and discuss progress to make sure it was all effective. Our primary mission was to record the pressure and temperature, of course, at different altitudes. The secondary mission was to obtain a set of thermal and visual images during the descent, which we could link together to create a thermal map of the area. We also measured location, velocity, and orientation. We chose the secondary mission because we were interested in how to create a thermal map and thus the potential, if engagement wanted to embark on interplanetary expeditions, we could discover life on different planets.
Okay, so we decided to use the T- microcontroller and transceiver because it fits so nicely. That was probably a mistake in the end because it didn't seem to like our IR camera. What else? So we had some ADAPRU sensors, which you can see. We've got GPS, and we had an accelerometer, gyro magnetometer. We've also got the temperature sensor and the pressure sensor, the primary mission. The IR camera, you can see, is the kind of black cylinder. That was given to us by Melexis. They sponsored us. They're the company who make them. They gave us 2 for free. So we've also got a visual camera nearby, which has just disappeared off the screen. But okay, yeah.
It's in the middle, bottom middle one.
So we decided to design our own PCB to organise all the wiring, which went pretty well. It was quite small, and you can see our circuit diagram.
But unfortunately, towards the end, a bit of the PCB ended up breaking because we tried to compress it. Some of the passive components ended up breaking, and we ended up only using part of the PCB and doing some external wiring. Okay. So from here, we also did lots of software aspect. I mean, we used Arduino for all of it, as I think did everyone, and because we tried to communicate with the T- board. We were also involved with the electronics team selecting the specific components so that the programming was simple, because certain components had specific libraries. Then we tested specific components, forming subsystems programs, and though unfortunately we were using an Uno for most of that, and then it made it worth transferring all of that onto the T- board. Though this process was very quick on some components, such as the temperature sensor, it was very kind of long and tedious for something such as the IR sensor. And we had a lot of issues with the IR sensor, especially reading from the sensor's EEPROM data and getting the calibration information from there. From then we formed a complete program which worked with the project which was on breadboard. And though the CAN code has since been refined to work with our base station software, it has largely remained the same, apart from the temperature sensor, which broke, and we had to replace it with one, which now uses a one-wire system. So it's actually slightly more accurate, so it's pretty good. We've also worked on the base station software. There was meant to be another image, I'm not sure you can see it, with just the COM ports stuff. But that's the base station software there. It's made out of Python because I decided it could communicate over serial quite nicely and work quite well. And it maps the IR data and it kind of graphs all the other interesting data, acceleration, gyro data, pressure, temperature, and it was calculated altitude, averaging GPS information, which we actually didn't get a fix on GPS, which is a bit irritating. We tried to expose the antenna, but we unfortunately didn't get a fix. But the program was set up to also use both the altitude from the pressure sensor readings and the GPS.
The colours you can see there, that's the infrared array, which we calibrated from yellow was very hot, red was very cold. That was when we were using the T- board, so as you can see, is meaningless. But that's what the array should look like in operation.
Basically what we found was even though it's communicating over SEL, therefore the code should remain almost completely identical, we managed to connect everything to the Uno and work perfectly, and yet connect to the T minus and not work at all, and we concluded that it was the T minus's fault, though obviously ours for not making sure it didn't completely work. And we're going to show towards the end a demo of the IR sensor working with an Uno. So I'm sure you will all eagerly anticipate that.
So we start off by making the process like can, and so it's made of layers of plates of formal ply held together with rods, and into these plates we located all the electronics. So in the top we had the temperature and pressure sensor, and so in the top we had the pressure, temperature and master switch, and in base we had the camera and IR poking out the bottom, which isn't there in the Uno board. So the shell in this one was made out of a thin plastic, but when we tested it, we found that teared on landing. So for the final one, we transferred to an aluminium shell, so it wouldn't be that.
Okay, so we tried to calculate the area we needed for the parachute, and that's how we did it on the screen. So we found this equation for the force by around the parachute, and we wanted it to go at terminal velocity, and we wanted that terminal velocity to be 10 meters per second. So from there we worked out the radius of the cross section of the spherical parachute, and then got the surface area. So then sort of cut it. So
this was also a fun opportunity to use some LaTeX, which was nice and fun for Tom, I think, who enjoys experimenting with this.
Just as you saw in one of the previous presentations, the drag coefficient for a hemispherical parachute is 0.8, but we had a hole in ours for stability, so we worked out the drag coefficient accounting for the hole, which you do by doing a ratio between the hole and the surface area of the parachute, which is why it's down to 0.75. Last slide, it's 0.8, which is the other way.
So for the parachute, we tested two possible designs. So we made the one with hole in, which we actually used, and one without, which was slightly smaller. And we found that when we dropped the one with the hole, it was slightly more stable, though not incredibly, but so we went with it for the stability. And we designed it so that if you look, the two top plates are directly connected to the parachute, so that for most of the time we were working on the can, we could have a complete can without a parachute, and then we could easily change over to those other two plates at the last minute to actually put the parachute into the can. So then that's us testing the parachute. So
This is all some pictures of the complete can.
so the top picture is the tearing open of the plastic shell after the testing, and so we transferred to the aluminium shell instead.
For ground support, we designed and built a UIV antenna, of course, and we went for a very simple three-element design, and it works, but not to a great extent. The range was only about 350 meters, so we used another one to support it, which we bought. But we wrote the base station software ourselves, and we got good results from it.
Ultimately, actually, both Yagis received good data throughout, but there was a little bit more noise from the one with our Yagi, but it was more of a precaution to make sure we got the data. We did have an SD card, but that ended up breaking just before our launch campaign, which we still haven't worked out why, but at some point we should try and see why it didn't work. But
Okay, this is all the data we got from some of the sensors. So temperature at the top, then we've got pressure, accelerometer and gyro. We've labelled 3 areas where we think that something significant is happening. We think at 1 it's been put into the tube. We think at 2 the launch is basically too small for us to see, but within the 2 sort of band, that will be the can falling and then hitting the ground, and 3 is then us picking it up. So you can see from the accelerometer data that it should have 10 meters per second downwards because of gravity. That's how our accelerometer works. But after it hits the ground at 2, the blue and so orange is Z, blue is X or Y, one of the sideways ones, they switch over, and so from that we know that the can hit the ground and fell onto its side. The pressure sensor data, we don't think we can get much from it. It was very noisy and not much was going on, but it was within the right area in millibars.
So what we thought is that to a certain extent the sensor was not accurate enough in one analog reading, one change in analog read. It was quite I think it was about a 1 millibar. I'm not completely sure. I can probably work it out. But that's what we thought it was. But that doesn't completely explain the complete random nature of the pressure sensor readings.
In testing, our pressure sensor was quite a bit more accurate. It sort of went to 0.1 millibars. So the fact that we have such great fluctuations here indicates that it wasn't so much a problem with the component as much with the wiring of the component as well. So, this is some pictures from our outreach. There's a beautiful website on the side designed by Ashwin. There was a slightly more colourful one, which I did, but this looks more professional, so I think we went with this. And it's got our blog embedded in it, which people who care could read about and stuff. And on our left here is the cake sale we ran to raise money for the project. I think we raised about £250, I think, which paid for all our components, which were under £150. And then we used some money to bring Ben here, because there's 5 of us.
Yeah, and that website's available at teamcolossus.com.
Yeah, just find it. On the upper left we've got our Twitter feed, and we also had Facebook stuff going on, but for the actual launch we were tweeting, and people could keep up with us if they minded. Also there's I don't know if the people at CanSat are affiliated with the people at Asgard, but the balloon sat they run, we ran had a stall in our school atrium, and there were lots of people who had come to that, and we think we may have influenced a few year niners, because they're now entering the Asgard balloon sat. So we feel like we've imparted some of our wisdom there, and they've been influenced by our reaching out to the community. We also are very active in our school SPS Space Society, where we go and do our CanSat stuff, maybe pass us by, peek in the door and say, ooh, what are they doing? Maybe I'll join in next year. So we feel like we've helped out there. We also had quite a good time talking to some companies, particularly Melexis, the company who gave us our IR cameras. We had a good email system going with a man called Luke Budgeons, who was very nice. He sort of organised our sponsorship, and yes, we felt we built a good rapport with a proper electronics company there, which we hope to develop on next year.
So now, because we didn't get any significant IR data in the launch, I just wanted to show that it actually works. So if it's all right, I would like to do a quick demo showing that the IR definitely works, and hopefully this will work. So I just dropped it. That happens sometimes. There we go.
So red is cold, and if we pointed at people,
Blue is the colour
should
one.
hopefully go yellow.
Yeah, if I point it. There we go.
So that is Ashwin in all his hot glory.
That's not
Oh, Ben? Alright, so that's Ben. The yellow's Ben, and it's got a fairly low refresh rate because the processor on the Arduino can't really keep up with all the algorithms it has to run to produce this. So it's about 1 hertz maybe.
Yeah.
But so this, although you could feasibly, if you're dropping from quite a high altitude, detect sort of life forms or sort of maybe a volcano if you were trying to land on another planet. And it'd be quite useful to know where the volcano is so you could strategically miss it. Because that could harm the satellite quite a bit.
Ultimately, it might be possible in the future to combine multiple of these multiple sensors to get a more reliable reading and make sure all of these things are correct. And also, the sensor does have the potential to get actual temperatures out of it. It was quite complicated coding, and my skills are not up to the mark. It was complicated as it was already. And
between 0 and 50 degrees Celsius, Melexis assure us they have an accuracy of plus or minus 1.5 degrees Celsius. So if we're looking for life forms, that can be really useful because life tends to be sustained, mammalian life at about sort of 30 to 40 degrees. So you can maybe even differentiate between types of life.
okay. So yeah, thank you very much. That's it. We wanted to get from the beginning.
Yeah, so we'd like to thank Dr. Patterson, who was sort of our mentor, guiding us, Dr. Weller for coming with us, and the 3 teammates who couldn't be here today because they had more important things to do because they're
I don't know what that is.
Nick, who was our team leader, Toby, who was part of the structural design team, and
Joe.
Joe, who was head of data analysis, which during our testing was very useful. And it's the great guys at Alexis, the UK's best microelectronics integrated systems provider. Go and buy all their things, they gave us free stuff. Any questions we'd be happy to take.
Just about the nice demo you just showed. I was wondering, what are the units on the Arduino?
Oh,
and what's the
that-
soft resolution?
It's raw, because also, if even it couldn't calculate temperature, it was miles off. And actually, when it was descending, there's a lot of IR absorption between by CO2 and H2O in the atmosphere, such that it wasn't incredibly accurate to calculate temperatures, and it would be even worse at a height, such that it's just reading raw data.
Numbers that sort of
Yeah.
So what we felt was most useful about it wasn't the exact temperature, but the relative temperatures.
Yeah, absolutely.
Yeah.
And what about the the resolution, the squares? How?
It's a 16 by 4. It's direct. We had one broken sensor, so last night they were having a lot of fun filing into that sensor and opening it up and seeing. So, do you know what happened?
Yeah, it's really cool actually. It's got an IR filter on the front of it, so if you look at it, it's reflective, so it only gets IR light in. And then by the thermoelectric principle, the front end bit is heated by the IR light and generates a slight voltage, which you can detect the heat temperatures on each one. It's a 16 by 4 array, but it's actually really small, the inside, so you could potentially have a large number of them to get a much more high resolution on the image.
What's the wavelength range response of the detector? What wavelengths does it work at?
I think it was 8 to 14 micrometers. I feel like that's something. Oh no, that was the filter. That was the filter. That was the filter they recommended.
So just above 14 micrometers, because
Yeah.
they tried to get us to filter out its 14
Yeah.
micrometers. We couldn't do that because an
It was
IR
about 300
filter would be very expensive to get that. It wasn't within our budget.
There was some
Ideally,
dodgy
we could have
ones.
had a filter between those wavelengths to get rid of any infrared re-emitted by carbon monoxide or gases in the air for the same effect. Yeah.
There were some dodgy Chinese ones, but I think from previous experience, the school decided we decided that we didn't want to waste some of the school's money and some of our valuable case sale money.
Yeah.
Okay.
Do the cakes taste good?
Well, yeah. Unfortunately, there was too many sales clearly that we couldn't have so much fun.
It was quite a management experience for us. There were about 900 boys to our school, and we had a 20-minute morning break in which to sell about 300, 400 of these things. And there were some very hungry teenage boys flying at us. So it was quite an experience. We thought it was quite fun.
Some people I know, some around here, baked some cakes and it was lovely.
Yeah, we'd like to mention
Sure.
our friend Quentin, who, although not part of our CanSat team, contributed to the cake sale, and so I feel deserves a mention. Yeah.
Who did most of the bake?
There was also
I
some,
wouldn't
there was
say,
also some
but,
Tesco
Hey, we did
Tesco
some things,
speciality and
Oh.
Tesco's finest cakes.
I made.
Yes. Some people did bake though.
My mum found out the next day and was a bit concerned about the flour.
With your camera and how you talk about your refresh rate being quite low, did you think about just saving the raw data and then processing it later?
Yeah, but
Obviously you
we
did
did,
it live.
and
It didn't work when it was in the can because of the whole T minus problem, but it didn't seem to work with the T minus. Here we're using an Arduino, but basically the one in the can, we could have saved the raw data, but it was all like rubbish. It didn't change at all.
it didn't read at all. It just we still have absolutely no idea because we wired up identically and we programmed
So
it.
if we had used a different microcontroller and got the data, we could definitely have saved it.
we're also quite interested in its application as a live use thermo camera because these things are incredibly expensive, but if you're trying to save money in your heating by finding the sort of heat sinks in your house, sort of the walls and stuff, you need a live update if you want to have to process it somewhere else.
Did you use special libraries for that?
They don't exist, unfortunately. It was a very long and complicated process to program it. There is a lot of sample code on the internet which is very useful, and I probably ought to have links with code I used, and it's on the top of my actual code. But there was some sample code which we had to adapt because it wasn't working and things have changed. A lot of it was using old I2C libraries which don't no longer exist, so we had to rewrite it for wire and stuff like that.
Melexis themselves are more of sort of an industry supplier company rather than like Adafruit, who sort of catered hobbyists, so they didn't have any software of their own. So we have to go through some quite dodgy, Stack Overflows, people trying to sample some code, and that's why we have to
Oh, that was amazing. Nothing dodgy about it.
it's quite backward.
Good choice.
Yeah, alright, thank you.